In the last section, we learned about the dot product. But there should be something that's kind of nagging you in the back of your mind. Why do we care? What is the use of the dot product? In the last section, we focused on just the computation of the dot product. But as far as we know so far, the dot product is only useful because it's only an interesting computational exercise. Okay. But in fact, it has some really useful geometric properties. And those properties, the root of them come from this theorem. Let u and v be vectors in Rn, and let theta be the included angle. Then the dot product of two vectors u and v tells you something very important about the cosine of the angle between those two vectors. It helps us learn about the angle between vectors. And let's make sure we know what angle we're talking about. Let's make sure we understand what this included angle is. So if we kind of draw a example picture, let's let this be vector u, and let's say this is vector v. Okay? Then the included angle is defined to be this angle here. Okay, that's angle theta. Notice, by the way, whenever we have two vectors, there's always two angles between them. There's the included angle, or the interior angle, and then there's the exterior angle. This one out here. Whenever we're talking about theta here, we're talking about the interior angle, or the included angle, which means it will always be less than 180 degrees. Okay, it'll always be 180 degrees or less. So we're going to prove this theorem. I'm going to prove this a little bit differently than how it's done in the book. In the book, it's a beautiful theorem, but it looks a little bit like magic. So I'm going to approach it just a little differently. So hopefully you could kind of understand why someone might look at this and get the result they do. Okay? So to do that, I'm actually going to complete the triangle here by drawing a third vector from the tip of v to the tip of u. And as we know from vector arithmetic, this is vector u minus v. Because I end at the tip of u, I start at the tip of v. So n minus start, u minus v. Okay? And what we're actually going to do here is we're going to use the law of cosines. Now, chances are you do not remember the law of cosines. You do not have to remember it here. Just know that we're using it. If you've taken pre-calculus, if you've taken trigonometry, at some point you've learned the law of cosines. You can look it up if you need it. It's a generalization of the Pythagorean theorem. So by the law of cosines, because we've got a triangle here, we can use the law of cosines. The norm of u minus v squared is equal to the norm of u squared plus the norm of v squared minus 2 times the norm of u times the norm of v times cosine of the angle between this side and this side of the triangle. Okay. Now I just want to emphasize that this is a generalization of the Pythagorean theorem. In the special case where the angle here is 90 degrees, if this were 90 degrees, cosine of 90 degrees is 0. And this whole side becomes 0. And so then we're just saying that the length of one side squared is just the sum of the lengths of the other two sides squared. Okay? But if the side isn't 90 degrees, then we have this extra term. Okay? Notice also we're focused on the lengths of the sides. So this isn't just u squared, it's norm of u squared. U squared actually doesn't have any definition. It's undefined. It doesn't make sense. Okay? But norm of u squared, that's the length of u squared. That makes sense. So we're dealing with the lengths of the sides. with the law of cosine, so that's why we need to take the norms of the vectors. Okay? So if you're a mathematician, you're looking at this and say, well, this is interesting. I really want to know more about the angle between these vectors. That would be very useful. So let's solve for this term. So if I solve for norm u norm v cosine theta, that means I subtract these over and then divide by -2. So I take this, I subtract this over, I subtract this over, I divide by -2, and that's going to, well, let me show you. So I divide by -2. I already have norm of u minus v squared over there. I'm going to subtract over the norm of u squared. I subtract over the norm of v squared. Okay, and that isolates this term here. Okay, because I'm going to go ahead and multiply that negative through, distribute the negative through. And so I'll still have a half in front. Negative's gone. Negative norm u squared, negative norm v squared, they become positive. So positive norm u squared plus positive norm v squared. And then this becomes negative. So minus norm u minus v squared. Okay. Well, now I have a lot of norms that are squared. So let's play with that. And one thing we know about norms squared that we learned with the dot product, and this is where the dot product comes in, is that if I have a norm squared, that's just the vector dotted with itself. So norm of u squared is u dot u. Okay. Norm of v squared is v dot v. And then norm of u minus v squared is u minus v dot u minus v. Okay. Well, that's looking promising. Maybe now I could do something with this. In particular, I'm taking a dot product of u minus v with u minus v. I could actually FOIL that out, because all foiling is I'm using the distributive law. And I know with the dot product, I can distribute. Okay? So I'm going to actually do this very carefully. So I'm using these very nice properties of dot products that I worked with in the previous section. So what I'm going to do is I'm going to keep this as 1, okay, u minus v, that's one vector, but I'm going to distribute this in over here. Okay, so that means u minus v dot u minus u minus v dot v. So I've left distributed in the vector. And I think I need one more parenthesis there. And now I'm going to do the same thing, but I'm going to right distribute. So let's right distribute vector u in and right distribute vector v in. So I still have u dot u here. I have v dot v. And so you really understand all we're doing is we're trying to simplify this right-hand side of this equation that we've made here, so we can maybe find a nicer expression for involving that cosine of theta. Okay, and so if I distribute, I get u dot u minus v dot u minus u dot v plus v dot v. And here I also distributed the negative, right? And now we could start combining terms. Okay, I have u dot u and I have minus u dot u. Those are going to cancel. I have v dot v, and then I have minus v dot v. Those will also cancel. And then the dot product is commutative. So v dot u and u dot v is the same. So I'm going to have minus u dot v here. I'm sorry, minus 2 u dot v here. And then an extra minus makes it a positive. So I get positive 2 u dot v. 1/2 times 2 is just u dot v. And I get my result. It's so nice. And so by just taking the dot product of two vectors, which is a really easy operation, just a couple multiplications, a couple additions, I could find something about cosine of the angle between those two vectors in any number of dimensions. And I do want to emphasize that. This picture, it's drawn in 2 dimensions, right? Because I'm drawing on a 2-dimensional surface. But whenever you have two vectors, they exist within a plane in 2 dimensions. No matter how many dimensions you live in, you can find a plane that goes through those 2 vectors. And so you could find an angle between those 2 vectors. So I've drawn it in 2 dimensions, but this would also work in 3 dimensions or 4 dimensions or 10 dimensions or 107 dimensions. You can find the angle between 2 vectors in any number of dimensions using the dot product.